Hi! Okay, if everyone could sit down. Sit down. Looking at you, Brendan Gregg, sit down. Okay.
And MCR.
Sit down, MCR. We're starting the lightning talks. Okay, so, hi everyone. My name is Fatima. Me and Jonah, we're the chair of the lightning talks. We have some really great lightning talks that we're going to do. So the format for tonight is basically all of these speakers were very lovely, and they applied, and we reviewed their talks and everything, so they're totally vetted, and they're going to be great. And each of them has 5 minutes to present, and then 30 seconds between each of them to hand off the mic and run up to the podium and stuff. And it's completely timed, so we're not doing any clicking at all, so that should be fun. And then after these lightning talks are done, everyone else gets an opportunity to do a lightning talk. So if you have a topic in mind and you want to talk about that with no slides, you can do that. Or you can spin the Wheel of Fortune and do one of the topics that I made slides for, which will be really fun. So if you're interested in that, start thinking about what you're going to talk about. But now we're going to hear from Elizabeth.
Hello. Oh, I get some extra time.
Hopefully
A few seconds.
20 seconds.
Well, first, I'm here to talk to you about mainframes.
Does this work?
Is it going?
It should be going.
How long?
I'm talking about Linux on mainframes.
30 seconds. There we go.
Right. So a year ago, I was looking for a change, so IBM came up to me and said, hey, you want to work on mainframes? And I was like, no. But then they're like, no, Liz, they're super cool. They run Linux. There's an open mainframe project, tons of open source stuff around them. So then I was finally like, okay, cool. So first question is what is a mainframe? It sort of depends on who you ask. You sort of think they run ZOS, as the implication has already been made. But you think of data and batch processing, all these amazing storage options. But these days they look like that one that was on there. Inside, they're all processing power. So there's CPUs and memory, but there's no storage inside of this. This is all just processing stuff. So you saw the one picture before of one single mainframe. That's a 19-inch rack. You can now put 4 of them next to each other, and that creates a really big one by today's standards. How it works with Linux, it can run either sort of on bare metal or on ZVM or now on KVM. So we're bringing more and more open source software into the realm, which is cool for me. But as far as history goes, if you go back to the 1950s, that's when the first white paper was written on time sharing, and that's kind of where the history comes from, is first time sharing had to happen on these big machines. The system called CTSS was developed in the 1960s. In 1972, ZVM was created. This was done on the System 370 machine. So this was really the first virtualization software that happened, and it still exists today in the form of ZVM. So, sorry IBM, but seriously, they were like, we don't need VMs. Who needs VMs? So this was late 70s when they weren't really putting much time into VMs. But it got better. In 1994, experimental TCP/IP support was put into the system, which sort of led the way for Linux being put on it. So in 1998, the first Linux port was created for the mainframe by a hobbyist group. They were just sort of having some fun. Some of their reasons, sort of the reasons that a lot of us got into technology, because it's there. This is like install Linux on a dead Badger era. So they were like, this is Linux, we're going to put it on everything. But then there were serious reasons, there's I/O and all kinds of fun stuff. So it turns out IBM was already working on a port when this came out, but the community said, we did one, and IBM's like, oh, well, I guess we have to push forward our plans. So at the end of 1999, for the 2.2 kernel, they came out with official patches that would apply to the kernel. They weren't upstreamed yet, but this still hit the news and was a pretty big deal because IBM was actually making an investment in Linux, actually releasing modules for the kernel for the S390. And I actually had to go to the Wayback Machine to pull up a bunch of these because these sites went away. So in 2001, they had this Heist commercial, if anyone remembers it. They were all about consolidation. So they were going into it, they were like, we really want to take an entire data center and put everything on the mainframe. So in 2001, they had an ad campaign all around Linux on the mainframe. And so in these past 20 years, they've really made advances in networking, storage. The processors are faster. They're like the fastest commercially available ones. And there's specific Linux processors that go into the Linux mainframes that are running Linux. In 2015, IBM released a Linux-only mainframe, which is the one way over there, and they've been getting smaller and more powerful as the years go on. Last month, released in September 2019, the one that fits in a 19-inch rack, so it's like a standard space. And IBM does not create their own Linux distro. Okay, we kind of do, because we bought Red Hat. But SUSE was the first one to be on the mainframe, so SUSE is actually like our original one. But Ubuntu's on there now. And this is like our fancy list of slides. It's a different architecture, so software needs to be ported to the architecture. So this is like we have a ton of open source software that we've already ported, but this is like our glamour slide of all the really important ones. So some things I learned. Google told us that we should all run on x86 hardware because it's cheap and it sucks, but it's cheap and it sucks. So also, things like Docker already have multi-architecture support. There was a talk about this earlier this week. Also, things like OpenSSL, it's not like some binary glob from IBM. You just put in a config file, and it works with the hardware crypto, which is super cool. IBM Cloud also has mainframes in it sometimes. So there's a few services in IBM Cloud that secretly run mainframes. The sales and marketing people hate mainframes, or the word, so they won't tell you. But they're totally in the cloud. It's really good at crypto, so like blockchain falling on our lap was amazing because it's really, really good at blockchain. And then the last slide, we are giving away free Linux VMs on mainframes. So if you go to developer.ibm.com/Linux1, you can get a free like 4 gig VM for like 4 months. So that is the last one. Thanks.
Okay. Hello, everybody. This room certainly filled up since I came in. All right. Okay, the 30 seconds was very generous. I take back maybe the snarky comment earlier. Plenty of time. I'm going to give a talk today called 30 Interviews Later, and it is all of the best bits of the 30 interviews I did this summer while looking for a new job. I'm Paige. I'm an SRE at LightStep. We're hiring. If any of these interview things sound wonderful to you and you would like to go apply, talk to me afterwards. So let's start the clock. Fun summer stats that I went through this summer. Interviewed with 6 companies. I did 30 individual interviews. I counted that as any time I had to step away from my desk and be at an appointment. And some other stuff that took over 6 weeks from start to offer. I'm going to talk about the best bits if you're an individual contributor. I think you can use this information to like raise your personal bar of what a good interview process looks like and what you want to go through. And if you're a hiring manager, please work with recruiting to improve the process at your company. So I just went through recruiter screens, tech screens, and then offer stage things that I liked. I work remotely, so if we are not going to do a video call, that's kind of a big red flag for me that maybe the company is not super remote friendly. Wow, these go fast. Things that I love, details about the interview. I want to know who I'm talking to. I want to know what we're talking about. I want to know where we're talking and when. Where and when people are normally really great about giving you. It is the who and the what that I think are important to include. Things I also appreciate, relevant questions related to on-the-job knowledge. I think SRE and infrastructure is obviously a huge, broad space, and so I want to know what I need to know for the job at hand. I love interviewers who put me at ease. I love interviewers who are going to give you in-interview feedback. They'll work with you. Both Greenhouse and LightStep did a great job about putting me at ease and saying I don't need to know all of the answers and that we'll be working together. There was actually true pairing, which I think is a wonderful sneak peek of what it would look like to work with my new potential teammates versus somebody kind of like sitting and watching me type and judging things. Actually pairing is wonderful. Diving into technical screens once we make it past the first bits, testing other aspects of engineering than just coding. One of the companies I really appreciated asked me to do a project plan of migrating their logging infrastructure, which is, I feel like I live in project plans most of the time, so it felt very relevant. Something that's maybe a little spicy take. One company had to capture the flag, which was the first time I'd ever done one, and I had like the best day ever. But I think there's maybe some issues with people needing to do out of work hours for that. On sites, I have some travel anxiety, and the companies were really wonderful about giving me an extra hotel night so I didn't have to fly in, fly out same day, which is like incredibly stressful. And again, this looks like a copy of the previous slide, but details, just directions to the office, how do I get there, what elevator, who am I gonna talk to, the interview title, and who I'm talking to, their title as well. Something LightStep does that I super love is every interview has two people. So we have two different perspectives on the same conversation. A lot of that is to mitigate any biases that can come up in interview feedback, and it's also great for interviewer training. My personal favorite is a 1-hour interview slot. That's enough time to come in, get coffee, get water, get settled, do introductions, and also give you enough time to work through whatever problems you're going to be talking about. And what LightStep did that was really wonderful is fiercely protected my time for questions so that I could interview them. They also gave me the email and contact information for interviewers so I could follow up on some kind of ongoing conversations. And probably the best thing in the world that they did was give me a handwritten card thanking me for my time, which I was honestly shocked. When does that happen that a company does that? Normally you have to write the cards and write the thank yous, and it was very charming. Great, now we're into offers. We maybe missed a slide, it's fine. I think the most important thing when evaluating an offer is to know the leveling information. 2 companies shared their engineering career ladders, which meant I knew where I was, and I wasn't going to be under-leveled. And they were super flexible with negotiation. Because I was interviewing at so many places, I didn't have the luxury of time on my side, and so when people were willing to take an early call or a late afternoon call, I really appreciated it. So, if you want to talk about interviewing, your wins, your woes, your great ideas, please come find me after this. Also, if you're curious about working at LightStep. Thanks.
Hi. So my talk is about how to SRE without an SRE on your team. So we're basically going to look at SRE as a function more than a job or a title, right? So how can you look at SRE as a process that everyone adopts? For those of us who don't know, I guess most of us do, SRE is Site Reliability Engineering. I'm Adwitiya. I'm the founder of Squadcast, which is a reliability orchestration platform. You can check us out on squadcast.com. So let me start by telling you what this talk is not. It's not going to tell you what SRE is or why it's important, problems that it can solve, or what a day in the life looks like. What it is actually a very easy getting started guide on, if you have no idea about what SRE is, how you can get started about it. So the first thing to do is, you need to understand that it's an evolution of your current process. So the first thing to understand is what are the metrics that you're monitoring and what are the important ones. So those important metrics can become your SLIs and SLOs. And I'll come to that a bit later. So once you understand what your most important metrics are, the next thing to do is understand what affects those metrics. So set some rules for the system, have an incident response process. And the third thing to do is document everything carefully. Now, choosing your important metrics, it's good to work back from your business objectives. So understand what are the metrics that actually affects user experience. And, for example, for a user-facing system, it could be latency, availability, and volume. So some things to keep in mind while you choose your SLIs, it should be a metric that's under your control. It cannot be an external metric. And yeah, of course, it's better to have fewer SLOs when you start with, maximum of 3 or 4 SLOs. The second thing is, of course, having a framework to understand what affects these metrics. So having some rules for how your system behaves, how mitigation takes place, and setting up an incident response process is, the next step of kind of adopting SRE. The third thing is, documenting everything. So document every failure and fix. So of course, you need to learn from your mistakes and your incidents, and you can't do that unless you're doing postmortems. The postmortem is just an easy way to start documenting everything. So just to get started with postmortems, it's easy to just pick one of the common templates and just start using that. And next thing, I wanted to share some best practices that teams have. So best practices, just to caveat this, people have their own best practices, but it might not work for you. So don't just like blindly copy something that somebody else has as a best practice. Otherwise, you'll be in the situation of Brian here, who's like 60% of the time it works every time. But yeah, so some of the best practices that we've learned other teams have is do not push to production on Fridays because mostly Saturdays are not working. After a push, make sure you hang around to check that it worked. And customer-facing teams should be aware of what limitations your system has, so that they know what to promise and what not to. Some things to keep in mind is don't give in to stress. On-call can be very stressful, and sometimes resolving an incident can take days. We all know this, and the easy ways to kind of help yourself is find some really good tools that take some of the load off of you, and find avenues of automation. So what are those tasks that you find yourself repeating again and again and again, and things that are simple and that can be just automated away, right? Don't burn out, balance your workload. A lot of people come close to getting really frustrated while being on call and doing SRE. So the important thing to remember is chill out. You got this. If you have your SLIs and SLOs in place, you got your metrics and your goals, and you have a process for response, and everything is being documented, then at the end of the day, you'll come out better. You'll be more reliable. So some useful resources out here, but you need to understand that SRE is a journey. It's important to learn from others, but at the same time, take everything with a pinch of salt, because what works for other companies might not work for you. So understand the core logic behind why people do things a certain way, and then apply that logic to your situation and figure out how that might work. Yeah, that's about it. You can email me at squadcast.com. Maybe a couple lines about Squadcast. We're building a platform to take SRE to organizations of every size. So help teams adopt the core principles of SRE, and doing that by evolving their own existing practices. Thanks.
So, hello everyone. I'm Jainam Shah, and I am an undergraduate student at IIT Ropar, India. And this is my first talk, so please smile looking towards me. Okay, so I'm going to talk about hospital. So, what is hospital? As the name suggests, it will run a script when a known fault occurs in a system. It will try to fix or prevent the system or the fault. So let's understand how hospital works at a high level. An application is running on a VM. So a monitoring system is going to monitor that application, and upon failures, it will notify the hospital that this failure has occurred. The hospital's agent, called surgeon, is sitting on the VM, and it will keep on polling hospital, and if any failure occurs, it will just run the script and try to prevent it. So, what is hospital not? The script intends to prevent the symptom, not the root cause. At a load balancer level, the queue buildup is happening. So, the root cause can be a database slowdown, but the symptom can be cured by restarting the load balancer. So, why did we build hospital? Let's face it, all these applications that we make are not perfect. So, sooner or later, one application is going to fail, or a service is going to not able to handle the increasing load. And also, every developer is fed up of the late night pagers. So, thus hospital will remove manual intervention, and it will automatically try to fix the failures. Also, it saves times by by fixing repetitive failures, and it ensures that the system is available every time. Also, machines are always better doing repetitive and mechanical tasks. And also, for a known failure, humans will not operate every time in the same way. Human may apply the runbook differently. And also, the feedback that also the machine will be quicker to fix the faults than humans. So, what is the present scenario? Let's say your load balancer is running and a monitoring system is checking its metrics. So, if a fault occurs, the monitoring system will alert the developer via pager and developer will try to fix it. And in the pleasant scenario, the hospital will receive the alerts and it will fix it automatically. Thus, with hospital watching, the developer can sleep peacefully. So this is the graph of an alert of queue buildup in an load balancer and the time taken by a human to fix it and the hospital to fix it. As we can see, the mean time to recover of hospital is less. So let's understand how it works. Mainly it is broken into two parts. There is a central hospital fixing for all VMs, and on each VM there is a surgeon. So the monitoring system will set up alerts to hospital's API, and upon receiving the alerts, it will prescribe a script to the VM. And the surgeon sitting at the VM is ready to perform the script when an alert occurs. Also, surgeon is a lightweight process, so it doesn't take much memory of the VM. So here the surgeon is pulling the script from the hospital, instead hospital pushing it to the VM. This is mainly because of the security reasons. Hospital would need credentials to perform a script in the VM. Also, we have used long polling instead of short polling. Why so? Because it is very unlikely to occur a failure in the VM. And short polling may notify with some delay. Now, every script performed by the surgeon is reported to the user via Slack. And also, the user can see the summary that, yeah, when I was unavailable, these faults were occurred and it was prevented by hospital. So, the future of hospital. We can add securities to the script run by the security features run to the scripts run by the surgeon. And yeah, machine learning is constant. We can make this an highly intelligent system. So thank you for your time. And if you want to use the hospital, it is open sourced at Gojek Farm. Thank you very much.
Hello. Whoa, echoey. I'm Denise. I submitted my slides to Fatima like 6 days ago, which is a year in conference speaking terms, so I forgot what the slides are. So I work for Pivotal. That's something I didn't put on there because, 15 seconds a slide is valuable real estate. Anyway, I'm going to be talking about site reliability engineering for cats. I'm really pleased that Amiya earlier touched on site reliability engineering, so hopefully that means I don't need to dig too deep into that. So I know you're all probably wondering, well, I came here for the serious technical content. Why should I think about SRE principles in terms of cats? Or vice versa? Well, I think that cats actually have a lot to do with site reliability engineering. I'm going to tell you a story. So in April 2019, earlier this year, I got a cat for the first time. His name is Sam. He's not that small anymore. He kind of grew up a little bit because cats do that. He's very orange and he's very fluffy. And he doesn't like to follow rules. So you'll see in the corner, that's a cat bed. He decided that the human bed was where he was going to sleep. So I'm like, okay, I get it. Like, I get your game, Sam. So what I concluded from this experience was cats are unrelenting agents of chaos. the background image is, I drew this one listening to someone from Google talk about how they do disaster readiness testing, and their doomsday scenario is called Catzilla. So I think that tells you everything you need to know about cats. So anyway, for the next 3 and whatever minutes, I'm going to talk about 3 lessons that I learned from being a cat owner. I'm not actually a site reliability engineer, but I'm going to pretend that I am. Number 1, it's very important as both a cat owner and an SRE to set realistic and sustainable service level objectives, which are not the same thing as SLIs or SLAs. They're different letters, SLOs. So in the beginning, my partner and I got this cat. We were like, all right, we live in a shared condo. It would be really, like, this common space. He shouldn't really go out into the hallway. So, like, no cat in hallway time ever. Cat stays in flat. We quickly learned that this is not really a realistic service level objective. Because turns out when a cat goes into the hallway and you chase after him, he learns, I get to play this fun game with the humans where they chase me in the hallway of the condo. So now we're like, all right, 99% cat in flat time. He gets 5 minutes to derp in the hallway each day. It's fine. So I think that when you're setting service level objectives, they should be ambitious enough to force you to learn and experiment, but not so far reaching that you spend all your time trying to hit those SLOs and not getting anything else done. So lesson number 2. It's very important as human beings to try to eliminate the toilsome work so that we can use our problem-solving abilities and work on higher-order problem-solving. Because, I don't know, running YAML, whatever. So when we first got our cat, we put his food in a little bowl as you buy from like Petco, whatever. And I learned that wow, this cat just knocks his food out of the bowl all the time. I spent all this time toiling and picking up food after him. And I was like, wait, I used Docker one time. I know the solution to this. So obviously the solution to every problem is just to containerize your workflow. Duh. Nothing can possibly go wrong with this. That's the end of that lesson. Really, just use Docker. So lesson number 3, as an SRE, recognize that shit's just gonna fail. And when, not if it does, try to optimize for learning above other things, like justice or blame. So there's a lot of research around this, and a lot of people are talking about I can't talk, too much wine. But rather than searching for root causes, I think folks at Netflix tell you that a more productive conversation is to ask, what are the contributing factors? And my friend Will, who works for Fastly, any Fastly people in the house? Woo, one there. I tried to convince Will to come, but he refused, because he was like, oh, Halloween with my family, whatever, some lame excuse. So Will says counterfactuals don't belong in postmortem. That's a good way to know whether your postmortems are blameful or not. And when I was doing research for this talk, I was asking people, I was like, SRE people, tell me about your cats. And Jason, who works at Shopify, was like, well, I try to focus on designing an environment where my old cat can thrive, because he likes to pee on things. So anyway. In closing, recognize that when you're running modern distributed systems today, failure is just an inevitable fact of life. It's ever present. So rather than trying to spend our effort avoiding failure, instead, we ought to design processes and tools that let us work on the things that are actually important. So take a step back, look at the big picture, try to understand what is the value that you're actually trying to deliver to your users, and set sustainable targets so that we can go the fork to sleep. No. There's a longer version of this deck at PromptConf, which has a picture of Jonah's cat in it. So you can look at that later.
Thanks.
All right, this is a lot more buffer than I expected to have. So I'm Michael Smith. Guess I'll start early. I'm a developer at Puppet, and I've been working on something called the Wide Area Shell. And this is a shell for dealing with cloud-native infrastructure. And so I've taken an interest in a bunch of different types of shells that interact with remote systems. And this is just kind of be an exploration of some of them. So first, what kind of properties do we expect from a shell? We kind of expect quick feedback, something we can play around with. It's text-based, so you can kind of reuse it, share it, rerun it. Provides direct access to some sort of system operations rather than being a self-contained environment. It's designed around being able to, generally they're designed around being able to write quickly, but not necessarily focused on readability. And they provide a hierarchical context and a sense of space for the place for the things that you're doing. So first one, starting in Windows 2000, Microsoft shipped NetShell that is for configuring networking things on your system. And so it can do interfaces, DHCP, et cetera. It can also log into other machines and configure them remotely. The shell provides a couple of things. It's showing that right now it's operating on a remote machine. It's dealing with IPv6 interfaces, and that context gives us kind of shorter command invocations. Windows Services for Management is a PowerShell provider. And by being a PowerShell provider, it gives a familiar language to build on. It's similarly kind of doing Windows configuration. Anyway, here's a couple of other examples. And what I think is different about these from other command line tools is that they give you that hierarchical context to operate in. So when you're going and manipulating Vault, you have paths, and you can then go set and configure things based on that. So briefly, PowerShell providers let you take arbitrary data and represent it as a file system in PowerShell. And that's used by, it's extensible, so a bunch of different things, like VMware PowerCLI uses it, and it gives you all the normal file system operations. A whole other set of tools are focused on bringing remote file systems locally. So you mount something locally, you can then load those files in your editor, copy them around. Most of those are implemented on Fuse, which was incorporated into the Linux kernel and a number of other systems so that you didn't have to extend the core OS to add new file systems. So NSH, BMC's network shell, takes some of the ideas of SSHFS but adds execution. So you can change context into another machine by a path, and then every command you run there runs on the remote machine. It kind of looks like you're just SSHing and executing commands directly, but it's a little more complicated than that. You can reference other files on other systems. So you can copy something from host 2 over to the current context you're in. Or you can copy files back to the workstation NSH is running on with the special @ symbol. And there's a couple of other n-prefixed commands that operate on multiple machines at once. This is all built on BMC's administration of those systems. The wide area shell is inspired by a number of these things, but it looks at cloud infrastructure as being all API driven. So we can query those APIs to list and find out information about those things. That makes it easy to see what VMs and storage are available, for example. And then Wash exposes files in those systems, and as well as console output, logs, and a couple of other primitives, like being able to execute things there. Wash also adds some more complicated queries based on metadata and attributes of those systems. So you can run a find command that says, give me all the instances started in the last 30 days or created by a team. So why we love reinventing all these shells is kind of a question I'm still working through. But part of it feels like we love simple, composable tools. And the simplest way to compose them is kind of files. You can deal with pipes and things, but files give you a kind of a permanency that is hard to, not present elsewhere. Anyway. But I wonder if we have the right abstractions for dealing with all this. So whenever you're dealing with network latency, you're going to introduce caching. All those other things, we're reinventing them for a bunch of these different systems. Anyway, if you love these kind of tools, come talk to me. Thanks.
Kill time. All right, I'm Vanish Talwar from the monitoring team at Facebook. And I'm going to be talking about a platform we're building called Dr. Patternson. Come on. 30 seconds. All right. Yeah, so it's a platform called Dr. Patternson. It's really automated debugging runbooks. I can get started. So most of you here are familiar with investigating operation issues, and you know it's hard. So here's an example, an abstract example where you have a network of connected services, spread across data centers, serving traffic, say, from global sources. An outage happens, and we need to investigate and find the root cause. And it can be hard, because the problem could be in the service, it could be in a particular region, it could be a client issue, a network issue, a hardware issue, a dependency issue, and so on, right? What do? To investigate, we look at multiple sources of data, but more broadly, we have to navigate through a complex ecosystem, and unfortunately, today we have to deal with several disconnected tools, processes, data sets, and so forth. And to top it off, most of the investigations that we do today are usually manual. They use outdated runbooks or incomplete runbooks, that don't have a lot of tribal knowledge. Like, how many times has it happened that you've asked others what investigations they did, what metrics they looked at? So all the tribal knowledge is usually missing in the documented runbooks. It's a time-consuming process. We all know that. But worst of all, it's repetitive. It's usually the same steps that you follow over and over again. It can get boring, and it's also error-prone. And the result, as we all know, is like prolonged downtimes. It's on-call fatigue. So this is where Dr. Patternson comes in. Dr. Patternson is a platform that we're building at Facebook to run what we call analyzers. Analyzers are essentially automated debugging runbooks. So think of all the runbooks that you have in your wiki in text. Say if you take that wikis in text and you convert that into code, then we can run it in an automated manner whenever we want. So that's really what Dr. Patternson is. Diving deeper, Dr. Patternson has two sides to it. One is creating analyzers, the other is consuming analyzers. So just focus on the left side for now. Creating analyzers, as I said, the approach is to essentially codify the manual investigations. And to support that, what the platform provides is building blocks and APIs. So for example, we have APIs for querying the different data sources for metrics, for logs, and analyzing them. We also have what we call as analyzer chaining, meaning that we can create some common analyzers and reuse it. So we could have, for example, a common hardware analyzer for host issues, or a network analyzer, or a DB analyzer. So then what can happen is that for common investigation workflows, we can have the experts write these analyzers once and then share it across the company so that the other teams can just reuse those analyzers in their respective automation workflows. Okay. On the right side, consuming analyzers, what we do is that we take those created analyzers and then we integrate with existing tools and processes that the team has, whether it's through CLI or the various UI dashboards. We also have integration with alerts. So when an alert fires, we can automatically run a Dr. Patternson analyzer, and the result of the analysis can be posted back to the alert task or in the alert manager, whatever the team uses. We also have some out-of-the-box, high-quality analyzers for shared investigation workflows, so for shared service infrastructure or data pipelines, etc. So overall, like the summary, the key takeaways, Dr. Patternson is a platform that we're building to automate repetitive investigation steps. There's clear value for it, and we've seen clear appetite. People really want it. We are seeing a steep adoption of this within Facebook. More and more people are contributing to it. Good adoption and critical mass is building up. We are using a community approach. We're building a federation of these analyzers and integrating with existing people's teams, tools, and processes. And as for the future, it is very exciting because Dr. Patternson, we also call it Dr. P, really provides a way for you to embed these interesting, cool new algorithms to analyze operations data. And also, it provides a way to start collecting data about investigations that you can now use to understand and create a virtuous cycle of improving the investigation processes and improve system reliability overall. Thank you.
Thanks. Okay, so it looks like I got a couple seconds. So there's time for the pre-presentation poll. Who has heard of computational storage and computational storage devices? No one? Excellent. This should be informative, or at least I hope so. So I'm Dan Pollock. I'm the CTO of a small technology consultancy. I'm going to do what amounts to a Parlour trick, which is sort of an old-timey way to entertain folks. Really just a fancy way to say demo. Ignore the rest. So this is a computational storage definition. It basically is the storage networking industry's long way of saying CPUs need to be closer to storage devices. In fact, they need to be directly attached, and that eliminates I/O. These are some examples of how those computational complexes or compute complexes are attached to storage devices. Typically, FPGAs have been used in the past to provide those services, and they're not exposed up away from the storage devices. Those are hard to program, so we use regular general purpose CPUs. This is an example of what that sort of implementation would look like in the future. None of this exists today. So on the far end, we just have storage devices. We have a computational storage processor. We can get those to talk. That's harder. And they provide these kinds of services. There are other things there as well. There are fixed services, which are the things everybody's sort of familiar with, encryption, RAID, erasure coding, and then there are programmable services. Those are more interesting ones. I'm going to show you one of those today. It's an example. It's not actually going to work the way you think it's, or the way it's going to work with the hardware, but it's basically something that looks like AI inferencing. What's going to happen is the system is going to store some data and perform some inferencing on it, and some interesting things will happen there. All the components I'm using are open source, and these are what they are and where you can get them. So if you're interested in looking, you can see the OpenIO stuff. Obviously, everybody knows Python, and then the OpenCV stuff is an open project for computer vision, and it's pretty nifty. So what we're going to do is create an event-driven function. We're going to watch for the event when an object is created, and then we're going to count the faces in a bunch of different images and see how that works. I got ahead of the slides. All right, so the code is simple. There's basically set it up, function that counts faces from OpenCV, connect to the beanstalk to watch for events, sit there and wait. When an event comes in, count the faces, then update the metadata in the storage system with the number of faces in the image. I'm going to use these three images. From that side, far from me is easier, to closer to me is harder. So fewer faces easier, more faces harder. These are basically soccer team, sports crowd, big sports crowd. So this is the system. We're just going to check it, make sure it's ready. So all the parts are online. I have a demo container that I created because that's just stuff you got to do up front, but there's nothing in it. Yep, it's empty. So now we're going to store the images. And because this has to fit in 15 seconds, it's sort of an automated script that does it. There's the first image going in of the soccer team. There's the second image stored of the sort of larger or small, middle-sized crowd, and then the larger size crowd. So now that the data is stored, we can see it inside the object store, which is what OpenIO is. And there we go. We got 3 files in, and they have the names of the crowds and the Portuguese national soccer team. So here we go. It has drawn the green boxes around the faces, which is something OpenCV does when it recognizes a face, and it's counted them. This is a soccer team, so there should be 11. And when we take a look at the metadata, over there it should say faces, and there shows 11. So now we have more green boxes in a large crowd. We'll take a look at how many faces it found. So this one, something says like 15, but there's way more than that, so that's probably a bug. And then this one, there's so many faces that it actually scrolls off the screen when you take a look at the metadata, but if you scroll back, you can see there's about 199 faces there. So anyway, it's effectively stored the files, invoked OpenCV facial recognition to see how many people are in those photos, and then updated the object store's metadata, not just by storing the image, but also saying, this image has some number of faces in it, and now you can search the metadata in the object store and say, give me all the images with some number of faces in it. Because this only took about 4 minutes, I actually had time for questions, which I thought was like a normal presentation thing to do. So if anybody has any, I'll be willing to answer them. If not, I'm done. Thanks a lot. Oh, wait, we do have a question. Sorry.
How victorious do you feel finishing your lightning pocket tournament?
Oh, well, you know, it's just I built it in, so it was kind of like, you know, supposed to be that way. I don't want to eat his time, though.
And I need a few extra seconds here because I am actually going to be switching things up. I decided that 15 seconds wasn't good enough, so I'm going to 5-second transitions. So I hope that works for everybody. So let's see how this goes. Not only am I switching it up with that, but I'm going to be spending the time talking to you about college sports, which might also be a little bit different for this kind of thing. So particularly, I want to talk to you about the NCAA tournaments, but I also want to talk about a lot of the math that goes into it and a lot of the numbers that are available. So there's more than 10,000 institutions of higher learning in the United States, and about 8,500 of them offer some kind of athletics program. And this is split up across 5 primary associations, although there's also a whole bunch of regional ones that I'm not going to bother mentioning. The 3 biggest ones are the NJCAA, or the National Junior Collegiate Athletic Association, the NAIA, or the National Association for Intercollegiate Athletics. But the biggest one that you've probably heard of is the NCAA, or the National Collegiate Athletic Association. That's the one that you normally hear about. Now, even this one, though, is split into 3 different divisions. So you have D3, which is 443 schools, and they have D2, which is 314 schools, and finally you have Division 1, which is 353 schools, and is generally considered the most competitive. This is where most professional athletes are sourced from at some point in time. Now, not only do you have 353 Division 1 schools, but most of them run 24 different sports. So this is a ton of different athletes. But the one I want to talk about today is men's basketball specifically. Now, men's basketball has 32 different college conferences that take up these 353 different schools. Now, college basketball is most known for the NCAA tournament, which happens every March. It's often known as March Madness. What's really cool about this is this entire process actually takes 353 teams and has one champion by the end of this. But only 64 teams can even make the tournament in the first place. So how does that happen? And actually, it's 68 schools because there's like these playing games they do now that they just added a few years ago, but that's a little different. I'm not going to talk about it. So you have these 32 different conferences, right? And all the teams play in these conferences, and each conference has their own conference tournament. So if you're a member of this conference, you play, and you play, and you play in this tournament. If you win that, you get to go to the tournament. But that's only 32 teams, and we still need the other 32 to make the 64, but it's actually 36 because it's actually 68 teams now. So a room of people actually sits there and says, like, who are the other 32 teams that should go? And these are difficult decisions. So they need data. They need a lot of data to figure out who else should go to the tournament. So they use things called team sheets, and team sheets are literally pieces of paper that have a whole bunch of stats on them, like win-loss and RPI and net and quadrants, and I'll talk more about some of those later. But also there's always like the eye test. There's always someone who's like, I watched this team play and they seemed very good, so they should get to go. And all these conferences are also split into high majors and mid majors and low majors. And if you're a high major, there's a much bigger chance you get to go because your program is more recognized and has more data behind it. So how do you maximize your chances of going? And this is where out-of-conference play comes in. So again, there are 32 different conferences, right? And the way a season's split up is the last 2 months of the conference is in-conference play. And this means the only games you're playing are against other teams within your own conference. But the first 2 months is out-of-conference play. And this gives you the opportunity to play other teams that may build a better resume for you. So you know what your conference play is going to be ahead of time because it's just teams that are in your conference. Out of play, you do not. And this is actually very complicated because this means that the athletic directors and the coaches of all these teams need to go around and say, will you play us? Will you play us? Will you play us? Will you sign a contract with us? We want to play you. You got to find your own opponents for this. And this is a complicated process. Most teams don't know who they're playing up until a few months before the season starts, which is next week. But they got to pick the right teams to play because they got to make sure that the ratings go up because they got to maximize their chances to make the NCAA tournament if they don't win their conference tournament. So you got to know how this math works. So you got things like the RPI, which is pretty simple. It's like your win-loss versus your opponent's win-loss versus your opponent's win-loss. And you got things like Ken Palm, which is a lot more complicated math. There's like a 2,000-word article he's written about it at some point in time. And the net rating, which was just introduced last year, actually uses machine learning and looks at data over the last 20 years to determine, is this school good enough to get to go to the tournament? And this whole process is called bracketology. There are people who have jobs, titles of bracketologists. There are people who do this professionally. And if you go to bracketmatrix.com, there's 196 different bracketologists' input into who they think is going to the tournament this year. And the root cause of all this, it's capitalism. Because it's money. The NCAA tournament makes so much money off of TV contracts, and it's also money for your school, though, because if you win games at the NCAA tournament, your school gets more money, and schools want more money. But there's also money for you and me, because there's a lot of gambling involved. So look, the Super Bowl is considered huge, right? But there's only about $150 million bet on the Super Bowl every year. There's about $10 billion bet on the NCAA tournament every single year. And why is that? Because there's so many outcomes. With that many teams, you have 2 to the 63rd, which equals some number that's very, I don't know, 9 to something. I can't really remember. It's, oh, right, thank you, slides. It's 9.2 quintillion possible outcomes. So look, I hate that people don't think sports are nerdy because sports are so nerdy. There are so many stats and there are so many numbers, and more every day. Computers are being brought in. Mathematical models are being brought in. Machine learning is being brought in. Every professional team on the planet has entire staffs of programmers just to help them figure this stuff out. College basketball is cool because you go from 353 teams to 68 teams playing in a tournament and eventually down to 1 winner. And this happens in 4 months every year. In 4 months, you go from 353 all the way down to 1. I think it's pretty cool. I think it's pretty fun. And real quick, I want to add something. There has always been a problem. That was not 15 seconds on that slide. But no, this is actually a legit important ethical announcement, I think. There's always been a problem overhanging the NCAA and the fact that they do not allow their athletes to be paid fairly. Today, literally today, the NCAA announced they are changing this rule. Student athletes playing in the NCAA are going to be allowed to make money. That's awesome, and it couldn't have been timed better with my talk. Thank you, everybody.